Hi, this is a short introduction to vibrational mechanics and a brief description of the lab equipment used for practical activities. Vibrational systems can be found almost everywhere in engineering fields such as civil, automotive, or aerospace. There are three basic approaches, not only for vibrational systems but for different types of problems in physics. One is analytical, in which we produce a mathematical model of a particular problem. The second one is numerical, and when we sometimes need to use computational power to solve a problem. And the other one is experimental. This one is particularly the most expensive, but sometimes this is the closest to reality that we can get. And this is a very complex model to illustrate a numerical approach using software to model a vehicle. This could be a ANSYS or any other finite element analysis software. As you can see, there are several parts involved, and the more detailed the model is, the better the results will be. There are two types of vibrational systems, those ones that are free to respond to a first input and others that produce a constant response due to a cyclic or even a random force. So they are divided in free vibrational and forced vibrational systems. This is an example of a simple mass spring damper system. As you can see, M represents the mass of the system, C represents the damping coefficient, and K represents the spring coefficient. Throughout the course, you see this type of equation quite often. This is a differential equation. That's not the scope of this Microteach session, but this is basically the equation that represents a dynamic system that changes over time. Don't be afraid, because there are several approaches on how to solve differential equations, such as the Laplace transforms, or you can get a little help of software such as MATLAB. Notice that the result is 0 in this case. So this is a hint that the equation represents a free vibrational system. On the other hand, if the system is receiving an external force, this is no longer a free vibrational system. So we are facing a forced vibrational system. In many cases, this can be a cyclic force based on a sine or cosine function, such as f0, sine the frequency, and over time, or even cosine. So this is more common to happen as many systems are exposed to some kind of excitation, and they are more likely to occur. And notice that we are only modeling the system with a single degree of freedom, and in this case we only need to care about the displacement in only one direction, represented by x. But similarly, we can produce rotational models of the system. In this case, the variable changes from x to theta. The mass is now represented by an inertia, no longer by a weight. The other factors remain the same. And we can also model this type of system by applying an external excitation, but now this is going to be excited by a moment, no longer by a force. And to show the different results we can achieve by varying the parameters, let's take a look at this. And when we've got no damping, we'll find out that the displacement or the rotation is going to be like in A. So the mass will be continuously moving around the reference point. In this case, is the resting point. This is the typical case of a harmonic response, and remember that in this case, K is king. So it means that only the spring is acting, and we have the parameter C equals to 0. In B, we have a low damping case, so we have both parameters C and K acting, but the damping is not big enough to produce a strong effect over the system. So it's going to stop at some point, but we, in this case, cannot identify this graph. But in C, we have this case here, in which the damping factor is strong, but we can see that the system will stop moving in a short time. And we have D, which represents the strongest case for damping, and in many cases we don't have any K affecting the system, so this damping parameter is too high, and it basically absorbs all the energy applied to the system. But when we are dealing with force vibrations, we have to care about resonance. Every system has its natural frequency, and it can be found as per this first equation over here, and it relates the K factor with the mass of the system. The basic equation that describes force vibration can be rewritten by using separate mathematical transformations. This is another way to represent the system. Notice that in one side of the equation we have omega n, representing the natural frequency of the system. On the other side we have omega 0, and the omega 0 is the frequency from the exciting force. The chart shows a particular case in which the exciting frequency is equal to the natural frequency of the system. And in this case, the amplitude of the movement is going to be very high, and we're going to have high displacements regarding to it. So the system will have a high amplitude and its movement, and this could lead to a system's collapse. So we have to avoid the condition in which we get close to the natural frequency. So the exciting force mustn't have the same frequency as the natural frequency of the system. And finally, let's discuss about the lab equipment designed to illustrate the vibrational systems in the course. This is the TM155. It can be reconfigured to provide us a better understanding of both free and force vibrations. And this system is based on a rigid bar that is free to rotate around the attaching point on the left, and with a marker on the other end. And this marker is going to draw the response in a drum recorder. And then we can trace the bar movements and register the results. And we also have an imbalance exciter responsible for creating the cyclic force, and a damper to represent the damping C, and the spring to represent the factor K. There's also a control unit that we can use to change the frequency of the rotating mass in the imbalance exciter. In the proposed exercise, the first approach is to produce a model capable of representing the system we just reconfigured in the equipment. Then we can use numerical approach using MATLAB, for example, to get a numerical result and compare with the experiment. An essential feature is that we can relocate the parts in order to simulate different systems configurations. That's why this equipment helps us a lot to better understand how the items' positions can affect the final results. So we can adjust the items to check how the displacement of the rigid end of the bar is going to be changed. For example, we can set all the items except by the damping factor, and then we can retrieve the value found in the experiment to compare it by getting the specific information from the resulting graph, such as the response frequency, the amplitude of X, and so on. And as an option, we can also design a system like this to simulate rotational systems. In this case, we'd be interested in discovering the characteristics of the bar end immersed in the fluid. Then we can retrieve the value of the C factor to analyze things such as the fluid viscosity. And finally, we can use the data acquisition device provided by the same supplier and get access to user interfaces for more accurate visualizations. And for more information about how to model vibrational systems, just check out those books here on the left. And if you want to go more in depth about how to model structural systems, or if you still have difficulties with mathematical modeling, I'd recommend those two books here on the right, so you can have more references on your studies. And I hope you enjoyed this session, and thank you very much.